thank you organizers and all of you for being here. Well, my talk is more about subject in quantum field theory rather than gravity, even though this idea of modular invariance and completeness sometimes often appear in the discussions on quantum gravity. So this is a work we have done recently with Valentin Benedetti, Kawashigashi, and Roberto Longo in Rome, and Javier Magan that is here. So this is a plan of the talk. I will start giving kind of a precise definition of what is completeness. Completeness is something that is talked about many times in quantum field theory, but there is no kind of precise notion of what is completeness. And here in an algebraic context, we will show a definition of completeness that is related to this Hug duality in the algebraic language. And then from there, I will show how this completeness is translating for two-dimensional CFT into this idea of modular invariance. And I will show this proof of this using the range entropies. And then I will start talking about how much incompleteness you can have, and this is measured by some index of algebraic index there. And I will then use this type of ideas to have some selection rules for realization group flows in 2 dimensions of minimal models. Then I will show some cases of infinite index, what happened there, and some results in higher dimension that are of the same flavor as these 2-dimensional results. So let me begin with this idea of Hug duality violation, let's say. So first of all, we are going to define something that is non-local operator. What is a non-local operator? So suppose you have a region like this ring here in space. All my pictures will be kind of in space, not in space-time. You have this. You have an algebra assigned to this region, and then an operator you can say that is localized in this region because it commutes with field operators outside, with point-like operators outside. But you can also say that this operator is localized in this region in another sense. This other sense is that this operator could be produced locally by the field operator, some kind of, in the algebra of field operators, you can construct this operator. So you have two different notions of what is a localized operator in a region. One is that it is produced by local field operators, and the other one is that it commutes with local field operators outside. And these two notions of localization in quantum field theory, usually it can be the case that they do not coincide to each other. In order to be a little bit more precise, we can define the additive algebra inside the region as the algebra generated by field operators. So it's generated by small balls, let's say. This is what is given here. This symbol is generated by all these operator algebras there. And then we have another notion of algebra in the same region that is the one that is produced by the commutant of the algebra outside. These primes here is the commutant. It means the set of all operators in the space that commute with a given set of operators. So I'm using also R prime now for regions to denote the region that is outside. So this notion of maximal algebra is that you take the field operators outside, take the commutant of that, and this gives you this maximal algebra. And it can be the case, for example, this red-like line operator here, it can belong to the maximal algebra. For example, a Wilson loop will commute with the operators outside, and it could be the case that the Wilson loop is not produced locally by fields inside. So, and we call these operators non-local operators in the region R. So when you have that situation, yes.
technical question. So it looks like, if I understand correctly, the additive algebra is then not of a Neumann algebra. Is it not weakly closed?
No. All of these are von Neumann algebras, and all of them are type 3, 1, and all of them are factors, and so there is no distinction in that kind of sense.
Okay, even though this additive algebra is not equal to its commutant, or its double commutant.
No. It is equal to the double commutant. Yeah, it is equal, but is equal to the commutant of the additive algebra outside. So the structure is this. You have the additive algebra is included in the maximal one, and if you take commutants, the commutant of the additive algebra in one region is the maximal one of the complementary region.
I see.
And the commutant of the maximal one is the additive algebra in the complementary region. But if you take commutants again, you go back to the same algebra. But this idea of that the double commutant of an algebra is equal to itself, this is von Neumann theorem, it implies in this situation, if you have non-local operators to one region, you always have non-local operators to the complementary region. Because, for example, suppose that these two are equal, if you take the commutant, these two will be equal, because otherwise, taking the double commutant, this will be different. So it already implies you some feature that if you have non-local operators for one region, you have also non-local operators for the other. And it also happens, because of the double commutant theorem, it's easy to see that these non-local operators of complementary region cannot commute to each other, not all of them. Otherwise, the algebra will be additive and nothing more. So the story is that this idea of hard duality violations allows you to describe these generalized symmetries in algebraic terms. The algebraic symmetry literature usually talks about mappings of operators, some endomorphisms, and you can see that this algebra inclusions is always give you some structure of endomorphism. So there is a relation between these two, but what you get from here as a bonus is that if you have a generalized symmetry, you always have a dual one for the other region.
So this effect of non-commutativity of A and B is like a Aronoff-Bohm effect?
You can say that, yes. For example, for a Wilson loop, so a flux of a magnetic field and a flux of electric field, if they are linked to each other, then they do not commute. But then you can immediately have this idea of what is completeness there, and it's stated like this. That suppose you have a theory and the algebras generated by field operators, these additive algebras, coincide with the maximal ones. So, and it means that are the maximal ones compatible with causality, with the commutant of the operators, field operators outside, coincide with the operators that you can locally generate. So, and this idea is called in the algebraic literature Hug duality. Hug duality. When you have Hug duality, is because these two algebras coincide, so the maximal algebra and the additive algebra coincide. And here we are, in this idea of completeness, we are saying that we have Hug duality for the additive net. The net is just assignation of algebra for any region. So this is a kind of precise definition of what completely means, and then it means that there are no generalized symmetries, or more precisely the absence of non-local operators, and also the uniqueness of the assignation of algebras to regions, when you have that. And in order to connect this with the usual idea of completeness people talk about you have like a complete lattice of electric and magnetic charges for a gauge theory, something like that. For example, if you have a gauge theory, you have the Wilson loop that it will be non-local operator for a ring. But if you have charges for the same representation as the Wilson loop, then you can decompose the Wilson loop into pieces, into Wilson lines, making it an additive operator. So if you have a complete lattice of charges, you will convert your non-local operators to additive ones, and you will have Hug duality in principle in that case. So this idea is kind of precise way to say the same as people was using for describing what is a complete theory. For example, another example of Hug duality violation is if you take, for example, a theory that has a global symmetry group and take only the neutral operators. The neutral operators, and in this case, you will have a Hug duality violation for the region of two balls, for example, disconnected regions, because you have a charge anti-charge operator, and this charge anti-charge operator is neutral in the full theory, but it cannot be locally produced because you don't have the charge. So it cannot be produced locally by operators, neutral operators in the two balls. And in a complementary way, the non-local operator outside, in this region outside, that has a topology of a shell, let's say in 4 dimensions, is a twist. A twist, we will call a twist, some operator that implements the symmetry here in this region and do nothing outside. So it's a kind of a local implementation of the symmetry. So this operator, this twist, commutes with a neutral operator in the ball, but it doesn't commute with the additive, so the maximal algebra that contains the charge anti-charge. So if you have a global symmetry, you always can construct this, and you always have this structure of Hug duality violations. And here are some classification results. You can think, well, it's important that these Hug duality violations are dependent on the topology of the region that you are looking at. And then you can say, well, what are the possibilities? Well, for example, this theorem, this old theorem, Doppler-Roberts theorem, tells you that for dimension greater than 2, all incompleteness for regions that are disconnected or they are complementary regions come from this idea that you have a group and you have the neutral part under the group. So, and then it tells you already that if you have a Hug duality violation, you can complete the theory. You can enlarge the additive algebra, adding the charges, and this new theory will not have Hug duality violation for disconnected regions. So there is a way to complete. This completion can be fermionic. The charges can be fermionic. So, and this means that there are no non-invertible symmetries. If you look at it, non-invertible symmetries of zero-form symmetries for dimensions greater than 2.
Why are those the right words to use? I mean, I understand that by completing the theory, you can remove what looks like a non-invertible symmetry, but why do you say that the original theory doesn't have a non-invertible symmetry?
No, the one that, the complete theory, theory, if you think what could be the zero form symmetries, then you will say, well, if I take the neutral operators, the ones that are unchanged under these symmetries, then we will produce a subalgebra, and then we'll give you Hug duality violations for regions, and this theorem tells you that the only way that can happen is that if the original thing is a group. So if you have a Hug duality violation,
I see. Okay.
Yeah. So it doesn't mean that you can cook up some operators, some kind of twist operators that are non-invertible, but these are combinations of group operators, right? That can happen. For d equal to 2, the situation is more complicated, and then it includes possibility of non-invertible symmetries. And it's interesting that the incompleteness, now is this Hug duality violation for several intervals. This incompleteness can be in general lifted, as in this case, but in non-unique way, in several different possibilities, to have a completion that is for some model. And then for this type of regions that are like rings that correspond to gauge theories, if you first complete in this sense, in the sense of disconnected region, you complete first, and then you can see that all this Hug duality violation for rings always come from abelian groups. It has only only coming from abelian groups. So it's much easier structure in higher dimensions than in lower dimensions. So I have to do a remark here that this idea of non-local operator is a relative one. So, for example, a Wilson loop is a non-local, can be non-local operator in a ring in 4 dimensions, but it's a local one in a ball containing the ring, because, for example, in the Maxwell field, you can write down this Wilson loop as a flux in the middle of the magnetic field. And this idea comes from the fact that for balls, for simple topologies, you always, or almost always, have Hug duality. So it means that all operators inside, local or non-local, can be written in an additive way inside the ball. So really, the non-local operator idea is a relative one. But that means that ultimately all non-local operators come from additive ones in topologically simple regions. It means that if you want to construct, for example, a conformal field theory, the usual idea is that you have to give the field operators, all the field operators, the list of field operators with the dimensions, spins, and the OP coefficients, and this determines the theory. So it means, and this is again correct here, but then it means that there should be some imprint in this data of the fact that your theory has or has not Hug duality violation, has or has not this description of generalized symmetries. And one natural question would be how you detect from the data whether you have or not this generalized symmetry. From the beginning, it's a difficult question because it means that you have to have some kind of relation between the non-local operators and the local ones. For example, the simplest case, that is the one that I will consider here, is how to diagnose if a CFT data comes from the neutral part of other CFT that is bigger and has the charges, for example. No? All the constraints, the internal constraints of the data, the bootstrap data, it will also be satisfied for the neutral part of the theory. So you would like to know if you can enlarge, you can extend your theory in order to be complete in the sense of multiple disconnected regions. Yes.
Sorry, can you explain again what do you mean by all operators are ultimately generated by local ones? I mean, there are twisted sector operators that are not local. So
I'm talking about, you start describing your theory with an additive algebra generated by fields, for example. No? And then the fact that there are no local operators or not is already there. This information is already there because you have to take commutants in this algebra to see if it is there or not. So, and in particular, these non-local operators, for example, this Wilson loop that come from the commutants of the outside part, it's usually true that these are additive operators, so you can construct it locally with field operators and polynomials and limits from in a ball. So if, for example, the Wilson loop in a Maxwell field is just a flux, internal flux of the magnetic field. It's exponential of the magnetic field, the flux of magnetic. So it can be constructed locally with magnetic field. See, this is the simplest case. Of course, you have more complicated cases in non-abelian case, but this idea of Hug duality for balls already tells you that this can be constructed locally, and you can also go to the lattice and do this explicit.
So in your language, for example, if I take Ising CFT, I take this disorder operator that is twisted by the Z2 line, right? Would that be a local operator or no?
Well, what would be a local operator is the intertwined, twist anti-twist.
Right.
Sorry, the charge anti-charge.
Sure.
And then if you, it's like,
so it would be a local operator for you.
Yeah. So in that case, this picture. Suppose you have the neutral part of a theory, this charge-anti-charge operator, that is a non-local one here, is local in a ball containing the two charges, because it's already, you can produce it locally with, but the one that is non-local is, it doesn't exist in the theory, it's the single charge. This doesn't exist. In order to produce that, I have to enlarge or extend my theory. This is the DHR theory. You can extend your theory, right? Okay.
Thank you.
Sorry. Just with your example of constructing this operator from the ball, are we restricting to quantum field theory on topologically trivial manifolds?
I'm restricting to topological trivial manifold, yes.
And are those restrictions necessary for these theorems you mentioned here as well? I'm just trying to keep track of.
Yeah, well, the setup of this is in Minkowski space, yes.
Okay, thanks.
Okay. But it's important that all the features that you can think of a theory in a curved space with some topology are somehow locally produced if you take not topological and trivial region. So you can study the thing there. Because in the generalized symmetry literature, people tend to think more in the other way, that they put in different topologies the manifold. But there is a local structure, this hardware evaluation, that allows you to talk about these things in flat space. Okay, then the question I want to address is how to see this imprint of hardware violations of non-completeness, generalized symmetries in the bootstrap data. And I will go to the simplest case, that is a CFT in 2 dimensions. And for in 2 dimension CFT, the question can be answered completely, and is this completeness is equal to S modular invariance of the theory. This modular invariance is something that, of course, is very well known in a long time ago. And if you go through at least from my point of view, that are kind of outsider, if you go to the Di Francesco's book and read what is modular invariance, then somehow you start the introduction and you end up with the idea that is I recommend you modular invariance because it's nice and whatever, but a few pages later it's like a universal axiom. So and there is no transition in the middle, so nobody tells you exactly what does it mean in terms of the quantum field theory itself. So well, there is also this problem that conformal field theories are also used for non-unitary theories, etc. Here I'm thinking in the interpretation of the conformal field theory only in terms of unitary relativistic theories, right? And then in that case, you can see that this modular invariance really is the idea of completeness, or in these terms, Haack duality for multiple intervals. Well, how you make the connection? Well, in the algebraic literature, it really was known some time ago. This was proposed by Rere in 2001, and it was kind of proved by Longo, Kawashigashii, and Muger, but this proof remained unpublished, and we have seen these things in the literature. They talk about this, but you go to the references and then they give you another reference, but it's never anywhere. And then we just wrote to Roberto and said, well, where is the proof? Where is the proof? He said, well, I don't know, perhaps Kawashigashii knows. And then he said, well, no, really, we didn't publish it. We didn't publish. So, and then we already have kind of a proof, a more physical proof using range entropies, and then we join forth and make this paper. So why the range entropies are useful to see that? Because they give you a connection of something that the range entropy is a Zenith entropy, something that you assign to an algebra or a state an algebra, and it gives you a connection with partition functions. That is the usual way in which modular invariance is described.
You're in particular not going to use the usual CFT logic of thinking of modular invariance as defining the theory on torus so that you can do plumbing fixture and so.
Well, I will show how you can. So it's important because many people, especially coming from string theory, will say that modular non-invariant theory is not a theory. Yeah, but I want to, in the sense of that there are good models for relativistic quantum mechanics. There are many non-invariant theories that are perfectly well defined, positive, etc., and it's perfectly well defined. So if you want a model of special relativity plus quantum mechanics, quantum field theory, I will call that quantum field theory. This is.
I mean, there's an elementary statement, right? There's the question of how do you define the trace on compact, on finite size, on finite regions. Just say theory on a finite space with a Hilbert space trace, that's a torus.
Yeah.
And that you can slice in many different ways, and that's the statement of modular invariance.
Well, I will show you that the partition function of the torus is well defined for these models too. For this model that are non-modular invariant. So, and it's very easy. A stupid thing to see what is going on here. Let me show. Then, well, let us think about the Ryu entropy. Ryu entropy is produced by some logarithm of the traces of the density matrix in a region. And then, for example, for one interval, it's very well known that for a CFT, there is a universal result in terms of the central charge and the logarithm of the region. And for two intervals, you can talk about the Ryu entropy of the two intervals, but it's better to think about this Ryu mutual information, where you subtract the Ryu entropies of the two intervals and the ones of the single interval, because it kills the divergences, it's well defined, and then in the continuous limit, and then because you have a conformal invariance, it's a thing that depends on 4 points. It depends on the cross ratio of these 2 points. So it depends on only one number, this number x, that is between 0 and 1. And then let me write this Ryu entropy, Ryu mutual information in this way. I'm just splitting some logarithm with the central charge and some u. So I did nothing here, nothing at all. It's just a renaming, but this is useful because of this. Suppose now that you have the entropy of these two intervals, I1 and I3, in a global pure state. Usually you would think that the entropy in the outside part is equal to that entropy, so you would have this relation. And if you plug this relation in all this calculation here, especially because of this thing, what you obtain, because of this symmetry of the entropies, you obtain this symmetry for the u terms here inside the mutual information. So it's equal for x and 1 minus x. But it turns out that this relation is not universally valid, because it's an equality between entropies of different regions, and the quantum mechanics doesn't understand what is the region. You have to say, this region for me is this algebra. And what happens is that for a global pure state, the entropies are equal for commutant algebra. So for this algebra and the A prime, that is a commutant. And here it enters this Hug duality violation. If the algebra for the outside part is equal or not to the commutant of the algebra of the two, is exactly this Hug duality or Hug duality violation. So you don't expect this property, you don't expect this equality if you don't have Hug duality, if you have Hug duality violations. If the theory is not complete, you will have that this property is violated. So this will be our let's say marker of Hug duality violation in terms of the entropies. For example, in this case, you have the chiral scalar, it's not modular invariant, it has sectors. This chiral scalar, you can have some operators that cross between, that is just the integral in the middle of the derivative of the scalar from one interval to the other, and this commutes with the local operators outside, but and then but cannot be produced locally in the two intervals because it has an integral over the outside part, and this is a non-local operator, so it violates Hug duality. And you can also see that because this A chiral scalar is just the neutral part of the chiral fermion under some U1 charge. Because of bosonization, these two algebras coincide, so it's the same theory. And then in this case, you can compute actually exactly this U term. I give you something that is not symmetric. In fact, all these U's are always 0 here because when this is eta, but this is x in my new language. When x is 0, is a very far away interval, so this U is always going to be 0 because of clustering. But then the thing increases when they touch each other. In this case, it diverges because we have many charges in this theory. But you can have theories with few charges, and this will be finite. This limit will be finite. So let me go then to the proof of this relation between the partition function and the replica trick. If you have the replica trick, you compute the traces of rho to the n, just putting copies of the manifold and gluing in a cyclic order. And here it will be important to have a range n equal to 2, because it's easier. And in this case, for only 2 intervals, forget about this third, you have 2 intervals and n equal to 2. It happens that this replicated manifold has genus 1, and it can be conformally transformed to the partition function of the torus. And this conformally transformation costs you it has some cost, but this cost is something that is universally given by some expression in terms of the central charge. So what you obtain from these papers, and people have discussed this in other contexts before even, that the range 2 for 2 intervals is equal to the partition function of the torus. Here L is the parameter of the torus, plus something that depends on the central charge, and the relation between the parameter, the temperature of the torus, let's say, and x, our cross ratio for 2 intervals, is given by these formulas that are quite complicated, but still the important point is that this relation between x and 1 minus x is mapped in the torus to L to 1 over L. So it's mapped to the modular S transformation. So when you extract from here the U term, U2 term, taking away some logarithmic term, you have this, and you see that this is symmetric under x 1 minus x. So from here you can compute the asymmetry, taking U2x minus U2 1 minus x, and this kills this term, and you get this exactly equality, that the asymmetry in the U of the range 2 for 2 intervals is equal to the asymmetry in the partition function, and this gives you this relation. This exists because this is non-zero because of Hug duality violation, and this is non-zero because non-modular invariance. So, and why? Why it happened? Because you have the torus. And the torus, if you see, this is identified with this is identified with this, you see in the other way it's exactly the same thing. But what happens? It can happen that your model, in order to define the partition function, you path integrate over some fields. But these fields may be the case that they do not belong to your model. So you need to put a projection in order to kill the charge operator, let's say. In this case, for example, if you take a complete model and then you focus attention on some neutral part, then you have to project over a neutral part, and this projector do the job, where these are the group elements. You are summing over the group elements. So immediately you see that the partition function will not look like modular invariant in that case. And the same here, in that case, when you have the projector, you have Hug duality violation because you have this non-local operator that is not producing locally because you don't have the charges. So, and then if you want to compute this asymmetry, it will be in general a complicated function of the cross ratio or of the modular parameter of the torus, but there is a limit, the limit of high temperature in the torus that coincides with the limit in which the two intervals touch each other, in which the contribution is quite universal and depends only on the symmetry, let's say, behind. So what happens? Suppose you are computing the partition function in the torus with this projector there, and then it means that you are thinking in your model as a model that is projected from a complete model that have all the charges, and then you take in the neutral part, and then your the ratio of the partition functions of your model to the one that is complete, this set C is the complete one, is just the expectation value of the projector, and this depends on the expectation values of all the symmetry group elements. And if you take the large temperature limit, what happens is that the expectation values of all the elements, the group elements, go to 0 except the identity, in which one case is 1. And you can think the reason for that is the fact that now your state has an enormous quantity of fluctuating charges. You have charges for all representations, and you can see that when you have many representation, many fusions of representation and sums of representation, this tends to some multiple of the regular representation of the group, and the regular representation of the group has a character that is proportional to this. It's only non-zero for the identity element, and this is the idea. But physically, you can think, yes, if I have a group element that is not the identity, a lot of charges will kill the expectation value. And then you have this limit for large temperature. You have this limit is 1 over G. And so when you compute the asymmetry, as I said before, if you go to x equal to 1 here, this will be 0, but U0 is 0 because of clustering. So what you need to compute is U2 in the limit of x equal to 1 when they touch each other. And then you can do this computation. This is equal to this asymmetry in terms of the partition function, but I added and subtracted the same for the complete model, but the complete model is modular invariant, so it doesn't make any change here. But then this piece is a low temperature limit. In the low temperature limit, the only thing that governs this partition function is the Casimir energy. They are both equal, so this disappears. And you get this limit of high temperature of the ratio of the neutral partition function on the complete model, and this from here you get log G. So this limit of the asymmetry, this is in fact the maximal value that the asymmetry takes, is given by some number that is universally given by the symmetry itself.
So can you explain your diagram? I mean,
sorry?
What is the red strip on your diagram? So how is it?
This is the projector. So I'm drawing it like a projector. So if charges go in this way, they will be killed. So, yeah. So it's just to say why the torus is different looking from one side to the other, right? Because you have a projector in the at time equal to 0, let's say.
So when you do modular transformation, then what?
It's not modular invariant, no.
So it will stay at the same place, but your diagonal, the rectangle will change, right?
Yeah, if you look at your rectangle from the two sides, it's not the same thing. So well, here. So this number here this is a special case where you project with a group symmetry, but there are these non-invertible symmetries in 2 dimensions. It can be the subalgebra of the complete one can be many different things and not necessarily related by a group. In these cases, what happens is that this is also again this limit of the symmetry is again given by some number that is coming only from the symmetry, but this is in general is called this index. So you have an algebra and a subalgebra. What you have in this situation, you have a conditional expectation that is a channel from the big algebra to the small one that is the identity in the small algebra, so it leaves the operators in the small algebra invariant, and it's a channel from one to the other. And with this conditional expectation, you can define a number that is called the index. In this way, this index is the smallest number that allows that this equality is satisfied. These are the positive elements of the algebra. This is just a mathematical definition. What is an index of an algebra and a subalgebra? The index is assigned to an inclusion of algebras. It's a completely kind of geometrical or algebraic number. And it somehow measures the size of the inclusion, how many times the small algebra is in the bigger one. Of course, it's kind of a heuristic explanation what it is. But in fact, here we can explicitly compute. I will show how to compute that. Well, here is an explanation, a little bit. I will go fast from that. That again, in the more general cases, you expect that the limit of the asymmetry is given by the logarithm of now a number that can be non-integer, that is this index, or people also call this quantum dimension. But in this case, we are talking about the index of the model and the submodel between these two things. But I mean the complete model and the model you are looking at, there is an index, but it's somehow not completely satisfactory, this formula, because you are talking about a theory without thinking about any completion. So here we computed thinking that the model is a submodel of a complete one. And this gives you the index of inclusion. But there is a way to talk about some index in the theory itself, that is the index of the algebra of the two intervals and the algebra of the maximal algebra of the two intervals. And this index is related to the other one because of this formula by Longo that give you this relation. So mu for a complete model is 1. So this lambda is just the square root of the global index by Longo, and then you can just express the result with something that depends only on the model and without mentioning any completion.
Yes, a question. So I understand that, so you take a modular invariant model and you construct a non-modular invariant from that. Does it also go the other way? So suppose I find a non-modular invariant model.
Yeah.
Can I always find a modular invariant?
Yeah, if well, the mathematical part of the theory that our paper has, the one given by Longo and Kawashigashii, they show that this is the case. But in general, they show that this is the case under the restriction that the theory is rational. In the sense, rational here means that the index. This global index here, that you can talk of the global index without mentioning any completion. This global index is finite. In that case, you can show that that there is at least one completion. In general, we show many cases that there are many completions, different completions. So in 2 dimensions, there are in general more than one completion. In high dimensions, it's unique. So let me go.
But there are cases then where the index is infinite, and you just find that this U2 is
infinite. It exists. Yeah. For example, if I will show some cases of infinite index, there could be different type of infinite index.
Since the proof of this, you said, went through completing the model, if mu is infinite, there is no completion. Is it also true that if mu is infinite, this U2 is infinite? Is that a theorem?
In the case of mu is infinite, the proof, mathematical proof that our paper doesn't hold because it's only for rational things. we have checked that in the case this mu is infinite because of coming from a group, then I will show some expression, but in general it could be something more complicated.
So in terms of proofs, there's an open possibility that U2 could be finite, but mu could be infinite.
No. In the case of infinite index, you will have U2 is infinite.
Great, thanks.
Let me move a little bit faster here. So, well, this is to say that for there are you can also study other range entropies. This was the case of 2 intervals and 2 copies, the range E2, and then you can say, well, suppose I have the partition function defined by a complete model, some integration of some fermions, some charges, or some fields, and then I restrict to some model. Then I have to, in the usual replica trick, I have to plug in some projectors in each of the boundaries of the replica trick. And this will be mapped to the torus as these projectors. These two, in fact, is a projector square, so it doesn't matter. You have only one. In the case of, for example, range 3 of 2 intervals, you have each interval is split into 3 pieces. You have 3 copies of the interval, and here, hidden there is the other interval. And then the projectors turns out to be one going around each of the handles. This is the case of 3 cases. But one of these projectors is redundant because if no charge can cross through here and through here, then no charge can cross through here. So one of them is redundant. So at the end, you have n-1 contributions of each projector, and then at the end of the calculation, this cancels with this n-1 of the definition of the range entropy. And so you get always the same result. All the range entropies has this limit when x equal to 1, that is, this is given by the index in all these cases. For the case of the entropy, so it was already known before. And then suppose you have a model and in conformal field theory, and you want to compute these indices, all that, then you can define your model by, you have the chiral algebra. The chiral algebra are the ones that are living on the null lines, let's say. The stress tensor is always there. You can also have other operators in the chiral algebra, and then you can compute these chiral characters, that is the partition functions only for the chiral algebra, let's say, and you have characters for each of representation. Then you can modular transform these chiral characters, and this give you the definition of these S and T matrices given by the modular matrices. And the model is defined by some coupling of left and right fields that give you the fields of your theory, and the partition function you build up with some coupling matrix times the characters, the left and right characters of the model. So in this language, that is the usual language, you have a modular invariance, is that this coupling matrix commutes with the S and T transformations of the chiral characters. So you have, this is purely chiral algebra thing, and this is what defines somehow your model, this M matrix. And you can see that this T symmetry, this T transformation symmetry, you go to the Francesco's book, and then you see that this is just the fact that the left and right dimensions different by an integer, and then this is related to causality because it allows you that these correlation functions in the Euclidean plane do not have cuts. So this is a necessary thing if you interpret your theory as a quantum field theory, local quantum field theory, so we have nothing to say about that. And then you can say, well, this global index is some limit of ratio of partition functions. You can check that in the limit of high temperature, and using the fact that your partition function is defined in this way, and the properties of your chiral characters, you can see that this limit is given by this number. So this is the global index of your model. It's a ratio. Here it depends on the coupling matrices, and these are the dimensions of the chiral sector. So it only depends on the chiral algebra. So if you have a model, you can go to this number and check what is the index. And here I have some examples. For example, you have the stress tensor for C equal to 1/2, and then you have partial completions, and you can have a fermionic completion or a bosonic completion. This is the Ising model. This is a free fermion. For the next possible unitary central charge, you have again 2 possible completions and many models inside. And then for the next one, you have 3 possible completions. One is fermionic, one is the diagonal one, where you plug fields with, these are all scalar fields, and these are also bosonic fields. This is non-diagonal completion, bosonic fields, but can have a spin. Though all these are modular invariant models, and how they are well understood and well known, but all this structure, all these are good models of quantum mechanics plus relativity, but are not modular invariant. In particular, the stress tensor alone is never modular invariant. And you can say, well, for higher minimal models, the things looks like it's going to increase, but it's not the case. You can find, for example, the submodels of the diagonal completions for all M, for all the minimal models are always 8, these 8 that are here. This was classified also by Kawashigashii and Longo in 2004, but they classified the subcategories, let's say the symmetries of this model, and we just look at, starting from the fusion rules of the complete model, we look at the possible submodels that close in itself, and you get this classification with all the inclusions. And here it's written, but it's very difficult to see. You have all these possible indices between the model and submodels and the global or intrinsic index of each model itself. And here you have some idea, some application to this. This is from this paper of last year. And there are also other papers with the different languages, but with ideas that they are very similar to ours. So, but the idea is that you have these submodels. Suppose now that you perturb your theory with some relevant operator that belongs to one of these models, for example, this one, but it doesn't belong to the models below, and it doesn't belong. It belongs only starting belonging to this. And of course belongs to the models above. But you perturb your action with this relevant operator, it means that you can think the normalization group flow is going on only in this model. You don't care about the complete model at all, or what happened above. So it means that the Haack duality violations of this model, all the structure above is related to Haack duality violation of the model, will be preserved along the normalization group flow. And if you end up in the infrared in some other conformal field theory, it must be the case that the whole structure up, the whole structure means the inclusions, the possible submodels, and the indices, all the indices of these inclusions will be preserved, and it has to be exactly the same as in the infrared. And you can check for a given central charge what are the structures in the models at low energy, and if you have a match or not. And this case is shown some very famous renormalization group flow that go from minimal model of index M plus 1 to the 1 M smaller. That is, it was discovered by Samologico. and you see that it matches perfectly well. So this is just a statement that the symmetry is preserved along the normalization group flow. All the above part is kind of the symmetry that is preserved, and this symmetry is destroyed. What is below is destroyed in the ultraviolet and reappears something like an emergent symmetry, different one in the UV. Here is not easy to see, but you have, for example, these non-diagonal extensions for the same normalization group flow, and you can see that this structure is preserved, and all this is completely different below. This symmetry is destroyed, and then something appears below. Well, and then let me briefly go through some infinite index cases. For example, if you have a Lie group relation between the model, the complete model, and the submodel. Now, before was you have to do expectation value of the twist, and the twist was expectation value at high temperature was 0 for twist different from the identity and 1 for the identity. Here you have a continuum, so you have to evaluate better these expectation values. For, of course, it will decay very fast away from the identity at large temperature, but it will have some Gaussian distribution of probabilities. And then when you compute with this the expectation value of the projection operator, it goes with it grows with the temperature like this, like a logarithmic term. When you write this in terms of the cross ratio parameter, you get that this as the intervals touch each other, you have a log-log divergence. And here, this G is the size of the Lie group. It doesn't matter if it's abelian or non-abelian because you are very near the identity, so it doesn't matter the non-commutativity. And you get this is kind of an imprint that your model is a submodel of a complete model with a Lie group symmetry. For example, for the chiral scalar, you have the explicit expression of this U. You can take the limit and you get 1/2. Here is exactly giving you the idea that you have only one generator, and in fact this is U1 fixed point of the complex chiral fermion. And for the Virasoro net of C equal to 1, with the character of the identity of the stress tensor, you have the explicit expression of the asymmetry. You take the limit and you get this 3/2 log-log. It means that there are kind of 3 generators. In fact, people have discussed this, that the Virasoro net for C equal to 1 is a neutral part and the SU2 of the chiral Cardinal algebra SU2 level 1. So you have again understanding this. For Virasoro net of C greater than 1, it seems you have too many sectors to be thought as charges of a Lie group. In fact, you have a divergence that goes like a log instead of a log-log there. But still, we don't know if this is correct or something in the procedure that we have made is not justified in this case, because we have an increasing with central charge, and as it's only the stress tensor. We do not know if this is correct or not. Something is wrong. And this model, this Virasoro net, so only the stress tensor for the C greater than 1, has some peculiar algebraic property that is called, it has not a strong additivity. If you take 2 intervals touching each other, the algebra of the big interval is not produced by the generated algebra by the 2 intervals. Somehow, this is generally happens, but here is like you have too many sectors, too many charge anti-charge in the big interval that cannot be produced by the other one. So it's some strange failure there that has to have some kind of input in this calculation. So, but let me go to some briefly 2 minutes? 1 minute. So briefly, in high dimension, what you can do, you would expect to have something for this type of manifold, but this type of manifold are not nice from the point of view of the bootstrap data, because this manifold is the one that has energies in terms of the conformal dimensions, and then you don't have a modular invariance, but we have seen that it is not necessarily modular invariance, but just to control the leading terms, and these people have explained that you can have an expansion that is understandable for the partition function high temperatures, thinking that the action is a local thing in this high temperature limit, and then you would expect that your partition function has the Stefan-Boltzmann term, high temperatures plus corrections that come from curvature, so it are spaced by 2 powers of the temperature. It means, for example, over 4 dimensions, you don't touch the constant term. It means now that if you do this partition function for a neutral part, it will get some constant term that is isolated and is the index, let's say. And then this means that you also can do it for the continuous cases, and means that trying to answer the question that I asked at the beginning, can you detect from the conformal data where your model is complete or not, in this sense of local charges? Well, it can. It's just looking at the spectral density, you can see some specific features in the partition function that tell you that some in this case, for example, some change in the usual Cardi formula in the expansion of high temperatures. So it depends on the density of states at high temperatures, at high energies. Well, and this is all. Thank you.
Okay, thank you for the very interesting talk. Are there further questions for Horacio? Yeah. Let's start on the left, and then we go towards the right.
Hello, thank you for the nice talk. I wanted to clarify something. I think I don't understand the fate of twisted sector operators in your...
Sorry?
I don't understand the fate of twisted sector operators in your formalism, so maybe that's where the puzzle is. But do I understand correctly that for you, for example, if I take a group, then the symmetry that acts on a Hilbert space is always the group symmetry? Whether or not, I mean, is this true? Because this is in tension with what, I mean, for example, in the other community, people say no, because and this is why I think twisted sectors are important, because if you say that the Hilbert space includes twisted sector operators, then it is no longer true that the symmetry that you're talking about is the group symmetry. It's something else. It has a name. It's called tube algebra. Actually, Muger, you mentioned his name.
No, I'm not saying. I have talked about a lot about group symmetry because it's easy to understand what's.
No,
but that's just an example of what it is.
No, I agree. But I'm saying even with groups, even if you start with the underlying symmetry data being a group, I just don't understand why the topological operators that you would call that implement the symmetry are still the lines of the groups, because this is not what we understand. For example, in twisted, if you include twisted sectors, this is why I said twisted sectors are, if you include twisted sector operators, then the symmetry that acts is no longer G. It is something else. It's tube G. It has a different dimension, different everything.
But perhaps what you say is the fact that suppose you have a model, and then some model is just a neutral part, right? And then you take the 2 intervals,
right?
And then you say what is the non-local operators? Then in 2 dimensions is different from higher, because in that case you have a charge anti-charge, but you also have the twist with the 2 endpoints going to the thing. So it duplicates somehow. Yes, you have this double.
No, yeah, indeed. Thanks for the comment.
Is this what you're talking about?
Yeah, my question was precisely about something like this. When you call neutral, you are saying neutral with respect to the group algebra.
Yes.
But I think this is probably in tension with just the fact that what some people would call a symmetry for extended Hilbert spaces is not the group algebra, it's a different algebra.
Okay.
So I just wanted to see,
Yeah.
do you agree that in your language?
Yeah, I understand that if the symmetry can have also, so it can have the twists and the charges at the same time somehow, yes.
Okay, so no.
Yeah, this can you see, you can see in 2 intervals, yes.
Okay, so I just wanted to confirm that you agree that what you say is different from what I said.
I don't know.
Yeah, I think
I don't know.
yeah, we can settle that discussion maybe in private. So I want to give other people the opportunity to ask questions.
Thank you for the nice talk. I have a question relating perhaps to the same field. So modular invariants are known to be in one-to-one correspondence with special symmetric Frobenius algebras.
Special symmetry for?
They're like special symmetric Frobenius algebras, and they like there's this work by Fuchs, Ronke, and Schweigart, which is rather old. I'm not sure
Can
if
you
you're aware.
repeat louder? I don't hear.
Special symmetric Frobenius algebras.
For what?
Frobenius.
Frobenius. Frobenius.
Frobenius,
Okay,
sorry.
It's my
My bad, my bad. So Haack duality seems to be equivalent to like it selects a modular invariant. And I'm curious about if it's known if the submodules are also in correspondence to some algebraic structure in that language.
Well, for example, it's known that it's not always the relation, for example, a kind of, I'm not expert on that, but it's known that it's not always, like say, a quantum group, something like that. It can be more general, the thing. And Frobenius algebra, for me, sounds like an algebra of fusion. Right? That is always there. Yeah, there is always an algebra of fusion, but these are some particular things, let's say. In general, for example, these algebraic people have can describe the general situation in the finite index with something that is called the Q system. Some particular elements and some particular properties that you have to satisfy, and that. But not all Q systems can be implemented or appear in two-dimensional CFTs. And for example, this index, for example, that I called is from 1 to 4 is discretized. So some specific number, this is shown index. For 4 higher, it can be anything. But for a smaller, it can be discretized. But it's known that some of the numbers cannot appear in conformal field theories, for example. But this is all this mathematical way. I'm not very familiar with all the details of that.
Yeah, thanks.
Okay, there was a question here.
Could you please clarify what is the relevance of the notion of completeness and Haack duality for the consistency of the original model? Because what I mean is the following: you show that in some cases when you have non-local operators, then maybe you can enlarge with balls this theory, some enlarged model which is complete, satisfy Haack duality, even if you have to project again back to the original model. But my question is, this is condition of Haack duality is necessary for the consistency or can be relaxed in some way?
Well, this is the point where I think most of people coming from string theory will say, no, it's consistency requirement. Even some papers that well-known people say that it's a unitary consistent, but this is not the case. It's not a unitary consistent requirement. You can have a perfectly well-defined relativistic and quantum mechanics models. The stress tensor alone, that is perfectly well-defined, and in that sense has positivity relation. Everything is perfectly well-defined in that sense. That is not more invariant. So it's not a requirement coming from, let's say, Wyman actions. It doesn't come from there. It comes from, if you want to talk about complete models, then in the complete model then is modular invariant. Usually you can complete, so there is no such pain in that. In fact, at least for finite index, you can say all the information is already in the submodel, because it's kind of bosonization idea, right? You have the scalar has all the information of the fermion because it's one particular completion, and the non-local the charge operators are in fact limits of charge anti-charge operator when one goes to infinity. So the sense of have all the information, all the operators are there already, and you have to take care in order, if you want to enlarge your theory, you have to take care that the charge operators that you choose commute to each other at special distances, and then they can be very different options somehow. Yeah.
Right. Okay. In view of the time, I think let's thank Horacio again, and then we'll be.